Good morning, after evening. My name is Júlio César and today's presentation will be about publication at the 1960 International Congress of Mechanical Engineering COBEM 2021, titled Quality Inspection Using Active Infrared Thermography with Computational Vision Aid Used in Composite Material of Wind Turbine Blade. Authors Júlio César Capistrano Estácio, Darlan Almeida Barroso, Marcelo Carvalho dos Reis, Jéssica Almeida Bessa, Alzuir Ripardo de Alexandria, Ceará Federal Institute of Education, Science and Technology. Introduction. With the advent of Industry 4.0, process automation and the replacement of man by machine have become a strong trend, attributing greater production speed and high reliability, which provides maximum quality to the final products. The concept of total quality has been a much addressed issue since the 1990s. Wind energy is seen as an excellent alternative to reduce damage to the environment, in addition to the immense availability of this energy source, considered inexhaustible. In this context, non-destructive testing techniques have contributed decisively to the quality control of wind turbine blades manufactured with composite materials. According to Maldag, computer vision can be implemented in hostile environments, allowing for greater reliability, faster process, and reduced rework losses. Types of failures, advantages and disadvantages of thermography. Du et al. 2019 classifies WTB damage into four types: downwind skin damage, main spar outer surface damage, non-visible damage, main spar internal surface damage. Advantages and disadvantages. No contact required, quick inspection, excellent bending tolerance, quantitatively determines the extent and rate of damage, provides real-time information, good reliability. Disadvantages are limited to online monitoring, affected by non-uniform heating, air humidity, requires thermal image processing, and not applicable for early fault detection. Objectives. This work essentially proposes the implementation of a post-active thermography technique based on concepts of the absolute thermal contrast method for the identification of artificial defects after the fabrication of a composite material of GFRP used in the fabrication of wind turbine blades. For this, a computer vision system is implemented through OpenCV routines in order to detect internal defects in GFRP samples. This process basically consists of the implementation of pre-processing, segmentation, and application of post-processing in thermograms with high thermal contrasts after imaging acquisition by means of an infrared camera. General concepts. Thermography techniques. In passive thermography, heat is generated by inspected object during its operation. In active thermography, an external heat source is required for inspection. Post-thermography and absolute thermal contrast. In post-thermography, the heat pulse generated by an external source causes a rapid increase in surface temperature due to thermal wave propagation, which diffuse into the inner layers of the material. Defect detection takes place in the cooling of the object. The inspection allows us to observe the instant of the defect when the absolute thermal contrast is maximum, which is related to the influence of the relationship between the mean diameter and the depth of the defect. Knowing that x and y are the pixel position coordinates, the absolute thermal contrast is given by the temperature difference between the defect region and the region without the defect. Material and methods. The infrared camera used in the thermographic test of model FLI E4 was configured for an emissivity value of 0.8 as it is the closest value allowed by the camera for GFRP with polyester resin of emissivity approximately 0.9. Focusing distance used was 0.3 meters. Samples preparation. Here we show the step-by-step instructions for making GFRP samples with polyester resin plus fiberglass blanket. Here you can see the flowchart of the methodology, which was divided into three processes: rehearsal, planning, experimental rehearsal, digital image processing. Digital image processing methodology, consisting of image acquisition, pre-processing, segmentation, scanning edges, recognition and interpretation. Results and discussion. The tree of samples are shown in figure. Each composite layer has a thickness of approximately 0.08 mm out of a total of 10 layers. Artificial defects were added internally to the samples with equivalent diameters of 6, 8, and 10 mm between and first and second layers, and so on the 10th layer. Acquisition of thermography images. The hot air blowed was activated for 20 seconds. Higher thermal contrast thermographic images were selected. Images were captured at approximately 2 seconds intervals. Pre-processing, Gaussian filter and image visualization, segmentation and post-processing, scanning edge detector red line. The unevenness of the external surface, that is, the lack of flatness and the lack of a better surface finish of the samples resulted in an excessive concentration of heat. A duct is needed to better distribute the hot air flow on its surfaces. Table 1. Values related to the composite layers of the GFRP samples. The diameters d, depth z of the artificial defects in addition to their respective dz ratios. Conclusion. In this work, it was found that it's possible to apply digital image processing together with pulsed thermography and absolute thermal contrast techniques for composite materials, although some improvements are needed. The results presented indicate that a final finish on the spacement is necessary to provide greater uniformity of heat rates in regions without defects, as the unevenness of the surface of the samples caused overheating at the T-types, making it difficult to detect defects. An evaluation of the effects of the relationship between diameters and depth was carried out, showing the good detection potential of thermography for thicknesses of 10 mm of the GFRP composite material. Reference. Thanks.